Binary notation is just another way of expressing values. Binary is used more because of hardware implementations, but really it doesn't matter for software. The value 20 in binary is the same as the value 20 in decimal or octal or hexadecimal. It's still 20. Now, due to, I guess you could say, historical reasons, the most used number system on planet Earth is the decimal number system. Most of this is covered in my bits video, but essentially the value 10 is equivalent to any base. So in the base 10 number system, 10 is 10. In the hexadecimal number system, 10 is 16, and in binary, 10 is 2. Very self-explanatory. The max value of any digit can only be the base subtracted by 1. So in hexadecimal, the highest digit would be 15. In the decimal number system, the highest digit would be 9. In octal notation, the highest digit is 7, and in binary, the highest digit is 1. Now, specifically in the case of hexadecimal, we had to invent more digits because we don't have any other digits past 9 since we universally use the decimal number system. So the digits for 10 to 15 are just A through F in the alphabet. Now, another way of trying to think about numbers is just trying to think about them as every digit is just the base to some power. And it starts at the 0th digit and it goes to the left in ascending order. So the number 932 in decimal notation is really just 10 to the power of 2 times 9, which is 100 times 9, which is 900, plus 10 to the power of 1 times 3, which is 10 times 3, which is 30. So now we have 900 plus 30 plus 10 to the power of 0, and since any number to the power of 0 is 1, we have 1 times 2, which is 2. So the full number is 900 plus 30 plus 2. And this also works for any other base. So another quick example with the number 1100 in binary. The leftmost 1 is equivalent to 2 to the power of 3, which is 8, multiplied by 1, which is 8. Then the next bit is 2 to the power of 2 times 1, which is 4, and the remaining zeros are just zeros. So if you add all of these values together, you get 8 plus 4, which is 12. So the value of this number is 12. In reality, nothing's ever going to be easier than reading decimal numbers since that's the way that our world runs, but it does get more intuitive over time. So now let's talk about how different numbers of bits are referred to. So the single smallest unit of value on any computer is called a bit, and then the next highest group of bits is called a nibble, representing 4 bits, then a byte representing 8 bits, which is also the smallest unit of addressable memory on any modern computer, then a word, which is 16 bits, then 2 words, which is a double word, which is 32 bits, then a quad word, which represents 4 words or 64 bits. And of course, the larger number of digits available or bits available in the number, the larger the number can be because you have more digits to use. In order to differentiate between positive and negative numbers, both signed and unsigned integers exist. The most significant bit in a number, or the high order bit, is the signed bit representing negative numbers in signed integers. In unsigned integers, however, we can represent the full range of values within a range of bits, while signed integers use half of the values to represent negative numbers. If you somehow run out of bits available in a number through arithmetic, then the integer will overflow and underflow, wrapping around to its maximum or minimum value depending on the situation. Signed integers are stored in what's known as 2's complement notation. So to get the negative version of any positive value in 2's complement notation, you take the number, you flip all of the bits, and then you add 1. This ensures that signed arithmetic always works and that you will always get one version of 0. Another interesting thing of note is signed extending and 0 extending. If a number is unsigned, it can be 0 extended to be converted to a number of higher bitness. The same is true of signed integers as well, except if the integer is negative, then you would sign extend by padding the number with 1s instead of 0s. Now, unfortunately, expressing values in binary gets very unwieldy after a certain point. Therefore, usually binary values are compressed or compacted into hexadecimal notation, which which is actually an even more compact notation than decimal notation, but it also converts to and from binary in a really easy way. And this is due to the fact that both bases are a power of 2, which means every 4 digits or every nibble is equivalent to 1 hexadecimal digit. So a byte or 8 bits can be represented by 2 hexadecimal digits. This chart is all that's necessary to convert to and from hexadecimal to binary. Due to the fact that the majority of human communication is done through written language, there's an entire encoding scheme just for converting letters to numbers and vice versa. So there's something called ASCII, and ASCII just represents all letters and all numbers with 8-bit integers. Each value within a range maps to a different symbol. And not only numbers and letters, but also other symbols are all represented within the ASCII encoding scheme. And you can in fact convert any ASCII integer into its actual integer value by subtracting or adding by a specific offset. Every data type also has a binary representation as well. In C, for instance, int is a 32-bit signed integer and unsigned int is a 32-bit unsigned integer. Technically, this can vary depending on the platform, but in practice, I've never seen this be different. And then also long represents a 64-bit integer. And in more modern languages, the bitness of different integers is more explicit. Strings can have a range of different representations. In C, for instance, strings are a pointer to an array of bytes, and a byte of 0 marking null termination. But in other languages, strings are represented by a pointer to an array of bytes and a length. Booleans are actually quite interesting because technically they only require a single bit of information since they are true false values, but in practice they're usually represented by a byte due to the fact that the smallest addressable memory on modern CPUs is a single byte, and accessing anything less than that requires masking out bits. Structs are really just data types next to each other in memory and a way of accessing related values in a structured way. However, structs also need to be aligned for performance reasons on modern CPUs, which means the size of the largest member is what the struct is aligned to. So if the largest field is a 64-bit value, then the size of the struct also has to be 64 bits aligned, which means it has to be a multiple of 64. Then of course you have pointers, which are also just word-sized or register-sized numbers holding the address of something in memory. And arrays are really just pointers to a contiguous block of memory, and really indexes are just syntactic sugar for offsets, at least in C. In other languages it might be different. I also forgot to mention that if the size of the struct doesn't satisfy the alignment requirements, then padding is added to ensure alignment. File formats are also just a bunch of numbers. Text files, for instance, are usually UTF-8 encoded, and every byte in the file corresponds to an ASCII character. Executables are a bit more interesting. They consist of headers and data segments and all of the opcodes to be executed in the program. And then of course there's images, and the bulk of image data is just pixel data with a byte used for representing each channel. Grayscale images, for instance, use one channel requiring 1 byte per pixel. RGB images have 3 channels with each pixel represented by 3 bytes, each being red, green, and blue values. Then there's 4-channel RGBA images with each pixel being represented by 4 bytes, with an additional byte used for the alpha channel, which represents transparency. And in general, all files can be hex dumped, and you could just look at what they're comprised of. So again, everything on a computer is just a number. But maybe the coolest part about it all is probably the hardware that implements